So hi, I am Koushik Loho. I am a postdoctoral fellow at HRI, Horizontal Research Institute. And today I'll be talking about these gravitational wave constraints on Barden primordial black holes. And this work was done in collaboration with Basubhendu and Oscar. So before beginning, let me thank the organizers for giving me this opportunity to present my work here. And let me start with sort of a word of caution that we have heard a lot about this memory wave signal. This is memory burden, this is something else. Okay, so when we talk about primordial black holes, these are a few things that I find interesting. So earlier you must have heard the lecture by Professor Tathagata. He has talked about primordial black holes as a dark matter candidate. And those are typically primordial black holes with initial masses around 10 to the power 15 gram or above. However, I will be talking about primordial black holes which are much lighter in their masses, and they essentially evaporate before the advent of the Big Bang nucleosynthesis. So the typical mass range for me for the initial mass of primordial black holes are between 1 gram to 10 to the power 8, 10 to the power 9 grams. So these kind of black holes, which I'll be calling the light black holes, those actually can evaporate via Hawking radiation and give you a particle dark matter. They can give you some some BSM particles which decay essentially and populate or give you the baryon asymmetry subject to if they take care of the Sakharov condition. They can also inject entropy into the plasma. They can, so especially if they at some point start to dominate the energy density of the universe, they can actually contribute to the Hubble. And of course, they'll produce gravitational waves, which is why I'm giving this talk. Now, the memory burden effect, let me tell you that so in Hawking's picture, we work in a semi-classical framework where the primordial black hole is classical object that radiates quantum particles. Now, this rate of mass loss that Hawking predicted has to be changed, sort of updated with the this back reaction effect that is caused by this quantum information that is retained in that system that acts back on the evaporation and leads to a stabilization of the primordial black holes. And this actually can be quantified as a function of the entropy of the primordial black hole. Okay, so most of you might be aware with this, but it doesn't hurt to check once that what are the important parameters that you must look into before we move ahead. And we have taken a monochromatic spectrum of black holes. That means the initial mass of all the black holes are same. And also there is this parameter beta. This beta is basically tells you how much black hole energy density was present at the initial time. By initial, I mean when the black hole was formed. Q is a fraction of m in when the memory effect kicks in. So basically, let's say if your Q is half and your initial mass is, let's say, m in, then at m in by 2, the memory effect kicks in. And this is also we treat as a free parameter. K is a measure of strength of the memory effect. What do I mean by strength? I'll explain in later slides. Okay, so this is the expression for the entropy of the primordial black hole, and this is the rate of the decrement of the mass for in the semi-classical picture. This is the reduced Planck mass. This epsilon is the evaporation function, and this rate has to be updated with this factor, where this S is the entropy and this K is its power. So in this sense that I mentioned, that K somehow determines what is the strength of this memory effect. And all these predictions or sort of speculations are enlisted in these papers, and you can check them out. And in this work, I'll try to constrain the value of K. So that is the goal. Okay, so let me sort of pictorially tell you what happens basically. So these solid lines are for the Schwarzschild black hole, and the dashed ones are for the Kerr black holes. To effectively communicate the central point of this paper, we need not worry about this. Actually, it suffices to only look at the Schwarzschild case. Now you can see the left one is for the semi-classical picture. You can, and these are all in log plots, and this is number of e-folds. So you can see that as it evaporates, it's almost some 10 to the power around 11 or something. That is the range. That is where how many e-folds it takes for it to evaporate. And in the memory burden picture, this takes a little longer. And we have taken the Q value to be half, so that is where you can see the stabilization. And we have actually provided some analytical approximations and done some analytical formulas. Those are there. But all this has been, all the plots has been produced using this publicly available package Frisbee. Okay, so now gravitational wave can be produced from primordial black holes, and that can be roughly categorized into 3 ways. So one is from the production of primordial black hole, one is for the merger of primordial black holes, and another is when the primordial black holes evaporate. So I'll be talking about the third case only, and these are things that are mentioned in this paper. And as basically the primordial black holes evaporate and produce gravitons, that can lead to gravitational waves. And because of this memory burden effect, that leads to an overproduction of the gravitational waves. So the amplitude you will see higher amplitude. But as you are producing more gravitons, that should actually create trouble with the delta N effective. So a way to account for, at least measure that is like this. So you can integrate over the GW spectrum over frequency, and that should be less than this value, as Ramkishore also showed, I think, this expression. But typically you will see that the gravitational wave, this omega GW is peaked around some frequency. So and if you integrate over it, it mostly picks out the values from that peak. So this approximation is justified in that sense, as long as it's not a very narrow peak. Okay, so what I'll do is that I'll use this information to constrain the gravitational waves or the excess of gravitational waves, which is a function of the k. So again, these dashed lines are for the curved black hole. You can ignore that, and these solid lines are for solid colored lines are for the Schwarzschild case. The delta N effective excluded. This is the solid line that is for the Planck. I have taken the value to be 0.34. I think this is updated 0 to 0.14 now, but this is for 0.34. CMB stage 4 predictions are 0.06. That is given by this dotted line over here. So you can see for and this k value 0, that corresponds to the semi-classical picture. And as you increase the k, you can see how it can actually touch sort of the delta N effective. So this is how it can be, this k can be constrained. Of course, and these are the benchmark values that I have used. Now, of course, you will be wanting to see a plot like this, where k is one of the parameters, and I have fixed q and beta and mean. So these are just 4 parameters I introduced at the beginning. And for delta N effective 0.34, this is the region that is excluded. That is the shaded blue region. And as CMB stage 4 will further probe this and can exclude up to this. We also looked at this parameter space from a bit differently, this time varying the beta. And you can see that for different initial masses, how it varies. One quick thing that you should not miss out is that you'll see that there is a flat curve, and then it sort of goes up. So the part that is solid is for PBH domination, and the part that is sort of dashed, you can see it here and you can see it here, those are for the radiation domination. So the conclusion is that the memory burden effect is quite stringently constrained and will be probed further by the CMB stage 4, with one caveat that there is PBH domination, because if there is no PBH domination, then you can see this can be relaxed a bit. And of course, you will find some relation of beta with that FPBH, but those are different things, because there you don't see an evaporation. Okay, so thanks. My thanks for ICTS for the hospitality, and I thank Recap HRI for the travel support. Thank you.
Okay, so questions, go on. Hello, Koushik. Thank you for the nice talk. So one of the questions I wanted to ask is, all these plots that you did was for q equals half, right?
Right. Yes.
Yeah. So like, do you have any intuitive idea about how it would change if we change the q, like as if you increase or decrease?
Yeah.
Okay. Not just intuitive. You have
Yeah,
very
so,
good ideas.
so this is the plot. If you change q, then you will see it like that. So we actually looked at from 0.4 to 1. If you go below 0.4, there is a problem that appears. So basically, you see this plot. So this is basically the plot of the mass as a function of the scale factor, right? The plot for the rho, that is the energy density for the PBH, will also see this similar curve, but there might be an intermediate domination of the radiation. That would rho radiation basically. So that would create some problems. I mean, you can check it, but it's a bit difficult to scan. So we ignored that part below 0.4.
So essentially, the fact that this omega GW reaches these high values are because of the PBH domination, I believe. Because when the PBH dominates at very low mass scale, then the graviton production is so high that eventually you get a big thing.
True, but even for let's say for lower betas, where the PBH is not dominating, we'll get some curve. It may not be as strong as PBH domination.
Thank you, Ghoshal.
So at some point you were talking about the stabilization because of the memory burden effect, like at q is equal to, let's say, 0.5. But there is also a possibility of classical instability.
Right? Yes. Those are not what we are talking about now. Those are the other possibilities. I have focused on this possibility, and this 0.5 number actually. So I'd like to clarify one thing. So many people actually think that 0.5 is the number, but it's not. So what the statement exactly says is that it has to be by 0.5. So it can be any values
between
like
1 to
above
0.5.
1 to 0.5, and 0.5 is also a rough number. It's only a ballpark number. It's not to be taken very like 0.5. It's not like that. Yeah. There is a mic, just I think there.
Hello. Yeah, it's okay. So you are talking about some analytical approximation also.
Okay.
But those analytical approximations are also valid for the spinning black holes or only for the non-spinning ones?
Okay. So no, I don't remember if we have given this for spinning
because
black hole.
If I understand correctly, the Hawking evaporation from the spinning black holes.
Right. You are talking about the evaporation function, right? So yeah. So I agree with you. But these all plots are from numerical solutions using Frisbee. So so these are exact in that sense. There are no approximation in the plots. So yeah. So all these plots are done numerically. But yeah, we just for some intuition, we have also provided some analytical approximation plots. But those might be just for the Schwarzschild. Yeah. Yes, Frisbee does include spin.
Typically, what value of the spin they take?
I mean, these are like extremal. So A star is basically your J, which is your angular momentum, divided by some G m square or something. Yeah. So basically, you normalize it up to. So 1 is extremal.
Okay.
So you can also. So basically, there is also an equation like you have dm dt here. There is an equation d A star dt.
Yes.
So that also is simultaneously solved given an initial A star. So this is the initial A star. So you can see here that they lose the.
So you are
A
saying
star very quickly.
when this these particles are emitting with an angular momentum, that is the reason spin also.
Spin is also going away.
Reducing. Okay.
Yes. So you can see it here. Actually, not very clearly, but you see this. After that, it follows the Schwarzschild case. So spin is basically gone by here. But there is another plot where we plot spin in x-axis and y and mass in y-axis. There you can see it very clearly. That is there in the plot in the paper, but I haven't included it in the figure. You can see it there.
Okay, thanks Koushik for this nice talk.
Yeah, thank you very much.
Let's